Young little minds, welcome to All Fours e-learning program. This is physics session number 45, right? So in this session we will learn about the potential, electric potential due to a point charge. Electric potential due to a point charge, a very important and a very useful thing. So better have a keen idea regarding this, right? So let's continue. Now we have started with electric potential. I was telling you, potential is the state of any electrical body. Electric potential is a state of a body which decides the direction of flow of charge, whether it is in a position to give charge or take charge. It determines the direction of flow of charge. It's a state actually. Electric potential is a state. Well, you can define this in terms of mathematical terms, like you can analytically you can define it as the amount of work done in moving a unit positive test charge from infinity to the point in the field. Electric potential V is defined as the amount of work done in moving a unit positive test charge from infinity to the point in the field. Work done per unit charge. Electric potential. Now we are going to make use of this equation in this formula to derive the formula for the potential due to a charge. So the definition for electric potential, it is work done per unit charge. The work done in moving a unit positive test charge from infinity to the point in the field. That is potential. Well, joule per coulomb volts, is it? So that is the basic definition we are going to use. We have learned in first year, we know work done is F dot S. You know this work done, W is work done F dot S. The dot product of force and displacement, this is Fs cos theta. Even this we are going to use in the derivation, right? We are going to have this also. And according to Coulomb's law, force between two charges F is equal to 1 by 4 pi epsilon naught capital Q's Q1 Q2 by R square. Even this also we are going to use. So these are the basic formula that are required to derive this formula for the potential due to a point charge. Okay, now let's come to our derivation. We have to now find a formula for the electric potential due to a point charge. Now first consider a point charge. Now this is a point charge Q. Now what is a point charge? I was telling you, any charge whose radius, whose size is negligible when compared to the distance of the point of concentration. Now I am considering a point P here, a point P. Let us say the point P is here at a distance R. So the distance of the point P when compared to the size is negligible. I can take a small spherical ball. A spherical ball where the distance is more when compared to its size, is it? So for all such thing you can have this formula, you can apply this formula. Now, so therefore let us consider a positive charge capital Q fixed at point O. This is fixed at point O, and at a distance R from it I am imagining a point P. Now I have to find out the potential of this charge at this point. So my derivation now is to find the potential due to this charge at this point, right? We'll do it. So how to find the potential? It is the work done on a unit positive test charge. Let us consider a test charge. I shall consider a test charge at infinity. Let there be a test charge Q naught, right? I am getting the test charge from infinity to this point P, right? I have to move the test charge from infinity to the point P. Now, so in the process of getting it, let's suppose I have come to a point A here, right? When I've come to a point A, let the distance of this point A be x. Now from A, I am moving the test charge through a small displacement to point B, dx. I am moving from A to B through a small displacement dx, right? So in between these two A and B are so close, so nearer that the electrical Coulomb's electric force between this charge and test charge and the charge capital Q is almost the same between these two. So the force on this charge due to this between these 2 points is almost same. There is no variation. Actually, Coulomb's law obeys inverse square law. As the distance changes, force varies. But I am imagining 2 close points which are very close, small distance between them dx, such that between those 2 points the force is almost same. The variation is in the third decimal. The variation is very less, negligible. Now, in moving the charge from here to here, let the force here, let the force. So according to Coulomb's law, we know the force of attraction repulsion between 2 charges F is equal to 1 by 4 pi epsilon Q1 Q2 by R square. Force F is equal to like this. So when the test charge is placed here, the Coulomb force on the test charge due to this charge. So the force on the test charge due to this charge, F. So force F is equal to 1 by 4 pi epsilon naught capital Q small q naught by the distance of the point at A is x square. Right? So I am moving a unit positive test charge Q naught. So Q naught test charge, unit positive test charge Q naught from infinity to the point A. When I am moving it against the electrical force of this charge, when suppose this test charge is at point A, the electrostatic Coulomb force due to positive charge plus Q on that F is 1 by 4 pi epsilon capital Q small q by x square. This is the force. First step. Now from A, I am moving the charge through a small displacement B, through a small distance B, right? So moving it through a small distance B from A to B through a distance dx. So I have already mentioned you, in between A and B are so close that from A to B at all these points the electrostatic force is almost same. No difference, almost same. So in moving this test charge through a small displacement dx, the small work done dw. Now we have learned in first year work done is force into displacement, F dot S, it is Fs cos theta. So the small displacement, in moving it through small displacement, the small work done is F dot dx bar. Both are vector, right? But the electrostatic Coulomb force is in the repulsive force. The electrostatic Coulomb force on this charge is repulsive, but the displacement is this side. These both are opposite. The angle between them is 180 degrees. The angle between them is 180 degrees. So therefore, substituting the small work done in moving this charge is F dx cos 180. Well, you know, according to trigonometry, cos 180 is minus 1. So the small work done in moving this is minus F dx. Right? Now substituting F here, the small work done in moving it is minus 1 by 4 pi epsilon naught capital Q small q naught by x square dx. So the small work done in moving the charge through a small displacement dx is this. Now I have to calculate the total work done in moving the charge from infinity to this point. Total work done. So if I take such small displacements dx like this, the small work done dw1, dw2, dw3, so on and so forth, the total work done, it is the sum of all, sigma or integration. So the total work done in moving the test charge from infinity to this point P is integral of dw from infinity point P is at a distance r. So therefore it is infinity to r. So substituting, the total work done is equal to integral infinity to r. The work done is minus 1 by 4 pi epsilon naught capital Q small q naught by x square dx. This is the total work done. 1 by 4 pi epsilon capital Q small q naught by x square. Now out of this, 1 by 4 pi epsilon capital Q small q naught is a constant. This is a Coulomb, this is a constant, Coulomb constant. Well, charge, our charge capital Q is constant. This is a unit positive test charge, it is also constant. So taking all the constants out, even the negative term also, so I get the work done as minus 1 by 4 pi epsilon naught capital Q small q naught by x, sorry, capital Q small q naught integral 1 by x square dx between the limits infinity to d, sorry, infinity to r. Our point is at a distance r. So this is the integration. Well, coming to the integration part, you have learned in your basic mathematics integration, integral of x power n dx is x to the power of n plus 1 by n plus 1. You know, integration, the opposite process to differentiation and integration, both are the reverse process. So integral x power n dx is x power n plus 1 by n plus 1. Suppose if I take the limits, let us say a and b, then when I substitute the limits, so you better remember, integral of x power n dx between the limits a and b, you can write as x power n plus 1 by n plus 1. Between the limits, this is the lower limit, this is the upper limit. Now substituting the limits there, so I get upper limit first, b power n plus 1 by n plus 1 minus the lower limit a power n plus 1 by n plus 1. Now this is the integration after evolution of the integration value. You have to substitute the limits, upper limit minus lower limit. So when I integrate this, so finally I get this. It is integral of x power n plus 1 by n plus 1 between the limits a and b is upper limit to minus lower limit, that is b power n plus 1 minus a power n plus 1 by n plus 1. Right? So you better remember this, the process you should know. The process you should know to deduce the formula for it. Now, so therefore, applying the same integration for this one. So this formula I can write it as, here. So the work done W is equal to minus capital Q small q naught by 4 pi epsilon naught integral of 1 by x square. It is x power minus 2 dx. Now I am taking the power from denominator to numerator between the limits infinity to r. Now, so performing the integration by this x power n dx, it is x power n plus 1 by n plus 1. So x power minus 2. So x power minus 2 plus 1 by minus 2 plus 1. So therefore W is minus capital Q small q by 4 pi epsilon naught. Now performing the integration by this x power n, this is x, n is minus 2. So x power n plus 1, so that is x power minus 2 plus 1 by minus 2 plus 1 between the limits infinity to r. Simplifying. So W I get it as minus capital Q small q by 4 pi epsilon naught. It is x power minus 2 plus 1 is minus 1. Here also minus 2 plus 1 is minus 1 from infinity to r. Well, again simplifying this, W is minus capital Q small q naught. This is test charge please, q naught by 4 pi epsilon naught into, now this is minus 1, so it is minus x power minus 1, I can write as 1 by x infinity to r. Well, this minus and this minus I can cancel it. So I get W is capital Q small q naught by 4 pi epsilon naught. Now substituting the upper limit and lower limit. Substituting the upper limit and lower limit. Upper limit 1 by r, lower limit minus 1 by infinity. Well, you know 1 by infinity, infinity is indeterminate. So 1 by infinity I can take it as 0. So this term becomes 0. So therefore the work done, continuing this, the work done W is equal to 1 by 4 pi epsilon naught here, capital Q small q naught by r, capital Q small q naught by r. This is the formula I have deduced. But according to the definition here, so according to the definition of electric potential, right? Now, luckily we have come on to the same point there. So according to the definition, the electric potential Definition for electric potential: it is the amount of work done in moving a unit positive test charge from infinity to the point of the field. So the electric potential V is W by Q naught. So potential V is W. We have deduced the formula for W as 1 by 4 pi epsilon naught capital Q small q naught by R by small q naught. So Q naught cancel. I get the potential as 1 by 4 pi epsilon naught capital Q by R. Now this is the formula for the electric potential due to a point charge at a distance R from it. Potential V due to a point charge Q at a distance R V, 1 by 4 pi epsilon naught Q by R. Right? So I shall again give you a brief clarity regarding this. You please understand, follow the things properly. So our derivation is to find the electric potential due to a point charge. Right? We are asked to deduce a formula for the electric potential due to a point charge. What is the formula? So now consider a point charge capital Q fixed at a point O. Right? This is the charge whose potential I have to find. Now I have to find the potential of this charge at a point P. Imagine a point P at a distance smaller from the point charge, from this point charge capital Q. Now, so to find the potential, what is the definition? Electric potential is the amount of work done in moving a unit positive test charge from infinity to the point in the field. So it is the amount of work done on a unit positive test charge. Now consider a unit positive test charge. So a unit positive test charge Q naught at infinity. Now work done in moving that unit positive test charge from infinity to the point. So I am moving the unit positive test charge from infinity to this point P. Now in the process of moving the charge from infinity, let's suppose I am at a point A. While moving from infinity, I am at a point A which is at a distance x, some arbitrary distance x. When I am at point A which is at a distance s, then there the electrostatic Coulomb electrostatic force due to this charge on the test charge is F. So the electrostatic force due to the point charge on the test charge 1 by 4 pi epsilon capital Q small q naught by, it is at a distance x square. Now from point A I am moving this test charge to a small displacement dx. The 2 points A and B are so close that the distance is so small that at all the points in between them the magnitude of the force is almost same. Very small variation. The variation is in the third or fourth decimal. So the variation is so small you can consider it to be a constant. It is a constant. So when the force is constant, we know work done. First year we have learned in first year work done. Work done on any body when I apply a force through a displacement, move it through a displacement s, then the work done is F dot ds. Well, the force is Coulomb force and moving it through a small displacement. In moving it through a small displacement, the small work done dW in moving it is F dot ds. F bar dot dx bar. Well, expanding, we know A dot B, AB cos theta, so F dx cos theta. Now, this positive charge is repelling our test charge, so the force of repulsion. But I am moving it against the force, moving it from infinity to this point, moving against the force. So the angle is 180 degrees. Well, F dx cos 180. 180 is cos 180, we know, minus. So work done is minus F ds. Well, now substituting for F here, if this is equation 1 and equation 2, so putting 1 into, so work done minus 1 by 4 epsilon capital Q small q naught by x square dx. Well, so yes, so the work done dW is minus 1 by 4 epsilon, substituting 1 into 1 by 4 epsilon capital Q small q naught by x square dx. Well, if I take such small elements, all the elements from there to here, and I have to find the total work, it is the sum of all, integration. So the total work done in moving the charge is integral of dW from infinity to the point P. So from infinity, the point P is at a distance r. So therefore infinity to r dW. Now dW I have substituted minus 1 by 4 epsilon capital Q small q naught by x square dx. Right? Now taking this constant terms, this is a constant, this is also constant, taking the constants out, it is minus capital Q small q naught by 4 epsilon 1 by x square dx. Right? So 1 by x square I can write as x power minus 2. according to integration, integral of x power n dx, I can write it as x power n plus 1 by n plus 1. Please note this formula, it is very important to remember. So x power n dx is x power n plus 1 by n plus 1. So performing the integration, minus capital Q small q by 4 pi epsilon naught x power minus 2 plus 1 minus 2 plus 1 between the limits. So minus 2 plus 1 is minus 1, minus 2 plus 1 is minus 1, right, between the limits. Cancelling minus and minus here, I get plus. So removing this minus, I get plus. So therefore capital Q small q naught by 4 pi naught x power minus 1, and writing it as 1 by x infinity to r, upper limit minus lower limit. So 1 by r minus 1 by infinity. So 1 by infinity, we know 1 by infinity is 0. So the work done is 1 by 4 naught capital Q small q naught by r. We know by the definition of electric potential, it is the amount of work done in moving a unit positive test charge from infinity to a point in the field. So potential is W by Q. So therefore work done, we have got this by Q naught. So dividing this by Q naught cancel. The potential due to point charge is 1 by 4 root naught capital Q by R. So this is the formula for the electric potential due to a point charge. The electric potential due to a point charge fixed at a point, at any point in its vicinity in the electric field at a distance r, the potential is V equal to, V is 1 by 4 pi epsilon naught, well it is 1 by 4 pi epsilon naught Q by R, where Q is the charge and R is the distance of the point from the charge, right. So therefore potential due to this charge, so potential V equal to 1 by 4 pi epsilon naught the charge Q by its distance R. This is the formula for the potential due to a point charge. Well, 1 by 4 pi epsilon, we know it is V equal to 9 into 10 to the power of 9, the quantity of charge by distance of the point. Is it? It is Q by R. Q is the charge there. Again, this is a scalar, right? Scalar, it has got no direction. Its units volts. Units is volt, joule per coulomb or volt. It's a scalar, but it can be positive, negative at 0. If the charge is positive, for a positive charge, the potential is positive. The potential is positive. So V is equal to 1 by 4 pi epsilon naught plus Q by epsilon naught. Plus Q by R it is. For a positive charge, the potential is 1 by 4 naught plus Q by R. Similarly, if it is a negative charge, it is 1 by 4 pi epsilon naught minus Q by R it is. So the potential V is 1 by 4 pi epsilon naught minus Q by R. For a positive charge, it is plus Q by R. For negative charge, it is minus Q by R. Right? Respectively to the nature of the charge, the potential exists. Potential can be positive, potential can be negative. Right? If potential V, now this directly proportional to the quantity of charge and the radius R. Well, of course, when R is at infinity, at infinite distance, here at infinity, the potential, when this is infinity, potential is 0. For any charge at infinity, the potential is 0. Right? Now, how about the potential at the location of at the point where the charge is located? Potential at the location of the charge. Suppose a charge is located at a point O. Charge is located at a point O, for example. This is the charge. What is the potential at O? Potential at the location of the point charge is not defined. You cannot define. Right? Of course, it will be infinity. Even if it is undeterminate, you cannot define. Indeterminate. So, we cannot define the potential at the location of charge. But according to definition, I am moving the charge from infinity to this point. So, in doing so, the work done to that point there, is it? According to the formula, when I put R0, then it becomes infinity. But it is indeterminate, you cannot define, is it? So we cannot define the potential at that location. Potential at any distance R, 1 by 4 pi epsilon naught, it is plus or minus. So general formula, 1 by 4 pi epsilon naught plus or minus Q by R. This is the potential due to a point charge, capital Q, at a distance R from it. Is it? At a distance r from it, the potential is like this. It is a scalar measured in volts. Well, I have given you the dimensional formula yesterday. ml square t minus 3q, sorry, I minus 1, right? Even though it is a scalar, it can be positive, it can be negative, and at infinite distance the potential is 0. So that way you find the potential due to a point, right? Now, coming to the application part of it. Okay, chalo, you solve.